The following is an Encore presentation of Everything Everywhere Daily.
One of the most important inventions in human history was artificial lighting. With the electric light bulb, the night could be illuminated, allowing people to extend the productive hours in a day and to work in places that were otherwise difficult or impossible. While the incandescent bulb was a breakthrough, it wasn't actually very efficient. It wouldn't be until decades later that a radically more efficient way of producing artificial light would be developed. Learn more about LEDs, or light-emitting diodes, and how they work on this episode of Everything Everywhere Daily. This episode is sponsored by Quince. No one is ever going to confuse me with someone fashionable or trendy. That being said, if I'm going to buy something, I want it to look good, be of high quality, and ideally be affordable. That is where Quince comes in. Quince is the kind of stuff you'll actually wear, like breathable flow-knit polos, crisp cotton shirts, and comfortable lightweight pants. In addition to clothing, they also offer a range of great items for the home and travel. Everything with Quince is half the cost of similar brands. By working directly with top artisans and eliminating the middleman, Quince offers luxury pieces without the markup. And I've told you all about the great items that I've purchased from Quince. From towels to blankets to a duvet, Quince has become my go-to source. Stick to the staples that last with elevated essentials from Quince. Go to quince.com/daily for free shipping on your order and 365-day returns. That's QUINCE.com/daily to get free shipping and 365-day returns. Quince.com/daily. This episode is sponsored by Fiji Water. You've probably heard of Fiji Water and have seen it in stores. Well, Fiji Water really is from the islands of Fiji. Drop by drop, Fiji water is filtered through volcanic rock, 1,600 miles away from the nearest continent and all its pollution, protected and preserved naturally from external elements. In this process, it collects a unique profile of electrolytes and minerals, resulting in more than double the electrolytes as the other top two premium bottled water brands, giving Fiji water its smooth taste. Fiji water's electrolytes are 100% natural, and this water even has a perfectly balanced pH of 7.7. I've recently been trying to reduce my consumption of diet soda, and I found Fiji water to be a great alternative. Visit your local retailer to pick up some Fiji water today for your next backyard party, beach day, hike, or even your home office. Fiji water is Earth's finest water. Before I get into LEDs and how they work, I should first take a step back to address the history of artificial lighting and why there was a need for LEDs in the first place. In a previous episode, I covered the history of the incandescent light bulb, so I'm not going to belabor the point, but the incandescent light bulb was indeed a huge breakthrough. The phenomenon of incandescence has been known for thousands of years. Basically, when something gets hot, it will glow and throw off light. This effect can be seen with a metal rod that's been put into a fire or even with hot wood embers. Incandescence works and is simple to understand, so the development of a working practical light bulb was more a matter of finding the right material to heat up and creating the right environment for it to incandesce in. Eventually, filaments that allowed for a bright, glowing white light were discovered. They were encased in a glass container that either held a vacuum or some inert gas that prevented the filament from burning up. For over a century, these types of incandescent light bulbs were the overwhelmingly dominant form of artificial light. This is the type of light bulb that most of you probably grew up with and are most familiar with. However, these bulbs had a problem. They were extremely inefficient. Most of the electricity that went into an incandescent light bulb didn't produce light. It produced heat and other non-visible wavelengths of electromagnetic radiation. Some of you might remember a toy called an Easy Bake Oven. The Easy Bake Oven was a children's toy that could actually cook small cakes and treats. The Easy Bake Oven used incandescent light bulbs as its heat source, which should give you an idea of how much excess heat was actually given off. Only about 5 to 10% of the energy used by an incandescent bulb is actually converted into useful, visible light. And lest you think that this heat might be a good way to heat a house, I assure you that it is not. There are far more efficient ways to heat a house, and in many parts of the world, the last thing you want to do is make a house hotter. In addition to being inefficient, the nature of incandescent light bulbs gave them a finite lifespan. Once oxygen got into the bulb, they would burn out, literally burning. Many alternatives were developed to solve the inefficiency problem with incandescent light bulbs. Most of these involve sending an electrical current through a gas such as mercury vapor. These types of bulbs, like fluorescent bulbs, are more efficient, but still waste 65 to 75% of their energy as heat. The ideal light source would be one that simply produced visible light and little else, something that could convert most of the electricity it consumed as light. And that is where LEDs come into the picture. LED stands for light-emitting diode, and they should not be confused with the similar sounding LCD, which stands for liquid crystal display. In addition to the similar sounding names, LEDs are often used in conjunction with LCDs. A diode is just a small electronic component that acts like a one-way valve for an electric current. It's made from a material called a semiconductor, which has been treated to create two different regions within the diode, one that has extra electrons, called the N or negative type, and another that has spaces for electrons, called the P or positive type. When electrons cross these regions of a diode, they can exhibit what is known as electroluminescence. In other words, the semiconductor will emit photons of light. Electroluminescence was discovered in 1907 by radio engineer H.J. Round of Marconi Labs, who was experimenting with a crystal of silicon carbide. However, the first true light-emitting diodes were developed by the Russian inventor Oleg Losev in 1927. Losev's discovery was published widely and known in many circles, but it was mostly considered to be a curiosity with no known practical purpose. There were experiments conducted on diodes and electroluminescence for the next several decades, but again, no physical products. In 1961, James Baird and Gary Pittman of Texas Instruments developed an LED that emitted light in the near-infrared part of the spectrum at about the 900 nanometer wavelength. The first LEDs that created visible light were all developed independently by three different research teams in late 1961 and 1962. The teams were from Philips Central Laboratory in Germany, Bell Labs in the United States, and the Services Electronic Laboratories in the UK. All three teams were working on totally different projects and arrived at somewhat similar solutions. Many of the different approaches used different types of semiconductors made out of different materials. And here I should note a problem with all of these early LEDs. The first problem is that they were all single wavelengths of light on the longer wavelength part of the spectrum. All of these first LEDs were some form of the color red. It was simply easier to create lower energy photons from this part of the spectrum. They emitted visible light, but it was far from white light that could replace general incandescent lighting. And the second problem was that the light they produced was very dim. That being said, there were uses for these early red LEDs. In 1968, the first mass-produced red LED indicator lights were made commercially available. They were made out of gallium arsenide phosphide by the Monsanto Corporation. You've probably seen any number of electronic devices that had a simple red light to indicate if something was on or off, and that was most probably an LED. They actually were the perfect solution for such simple lights. They used very little power, were cheap to make, and they almost never failed. In 1969, Hewlett-Packard introduced the HP 5082-7000. It was a series of LED lights connected to an integrated circuit and could display simple letters or numbers. It was the world's first digital display. In the 1970s, the price of LED dropped to under 5 cents for simple red ones. Further advancements in semiconductors resulted in the creation of yellow and green LEDs during this period as well. However, developing LEDs that produce shorter wavelengths of light towards the blue end of the spectrum proved to be extremely difficult. There were weak blue-violet LEDs produced as early as 1972, but nothing bright and nothing truly blue. The big breakthrough came in 1993 when Shuji Nakamura of the Nichia Corporation in Japan demonstrated a bright blue LED using gallium nitride as the basis for the diode. Simultaneously, Osamu Akasaki and Hiroshi Amano of Nagoya University were also developing blue LEDs. The development of a blue LED was actually a huge breakthrough. Nakamura, Akasaki, and Amano were awarded the 2014 Nobel Prize in Physics for their discoveries. Why was a blue LED such a big deal? Because blue is necessary to create white light LEDs. White isn't a color per se, it's actually a mix of colors. In particular, you can get it by mixing the primary colors of red, green, and blue. No blue light, no white light. That being said, just taking 3 different colors of LEDs didn't produce a very good white light. The better white LEDs were just blue or ultraviolet LEDs with a phosphor coating which created white light. The first white light LEDs was released by the Nichia Corporation in 1995. These first white LEDs that were commercially released in the late 90s were expensive, not very efficient, and had poor quality of light. However, through the first 2 decades of the 21st century, LED technology has continued to improve by leaps and bounds. The brightness of LED light has improved dramatically, the color of white LED bulbs has improved, and the cost has come down. The initial argument in favor of LED light bulbs was that even though they cost more, the reduced electrical consumption coupled with their longer lifespan made them a better deal than cheaper incandescent bulbs. Even though that was true, many people still balked at paying such a large amount for just a light bulb. However, within the last 5 years or so, prices have dropped to such a point that even the purchase of an LED bulb is a simple decision for most people to make. In my home, literally every light bulb is an LED bulb today. About 5 years ago, I made the switch and started to replace my incandescent bulbs with LED bulbs whenever one burned out. And just a cursory check over on Amazon.com shows that the cost of white LED bulbs is now about the same as traditional incandescent bulbs. In fact, the only reason why LED bulbs are shaped like bulbs is because that's how incandescent bulbs were shaped, and LED bulbs needed to fit into the older sockets. LED bulbs have a much wider range of shapes and form factors than traditional lighting. LEDs can come in strips, tubes to replace fluorescent lights, or even flat panels. And not only can LED lights come in a variety of shapes, but it's entirely possible to have LED bulbs that can display a wide variety of colors. The efficiency of LED lights is remarkable. One of the measures of the efficiency is the amount of lumens of light created per watt of power. So, for example, an oil lamp produces 1/10 of a lumen for every watt. An incandescent light bulb produces 16 lumens per watt. A fluorescent light bulb creates 60 lumens per watt, and a modern LED bulb creates 300 lumens per watt. The creation of efficient white LED lighting to replace incandescent lighting is not the end of the LED story, however, not by a long shot. One of the next big uses for LEDs is what's called micro-LED displays. Over the last several decades, enormous advances have been made in display technology. In fact, that's probably worth an episode of its own at some point in the future. There have been plasma displays, LCD displays, OLED displays, and others. Micro-LED displays have just begun hitting the market in the last few years. They consist of arrays of microscopic LEDs, about 1/100th the size of regular LEDs, that make up every pixel of the display. Micro-LEDs have big advantages over other display technologies. For starters, they use significantly less power. That means less heat and less electricity to run a display, which is extremely important if the display happens to be powered by a battery. They're also thinner, which means that they take up less space and are lighter. However, perhaps more importantly, they have the potential for much better picture quality. They're much brighter, have more contrast, and have deeper blacks than LCD or even OLED televisions. And if all of that isn't enough, this can be done on an otherwise transparent screen. The Samsung Corporation just demonstrated a transparent micro-LED display at the 2024 Consumer Electronics Show in Las Vegas, just days before I recorded this episode. Micro-LED displays are still new and are not widely available, but they should be one of the biggest technologies in the next few years. The barrier to wider adoption right now seems to be quality control in the manufacturing process. As with most technologies, the first micro-LED televisions will probably be incredibly expensive, and prices should fall rapidly afterwards. It's taken a while, but the LED revolution is just getting started. The adoption of LED lighting is increasing at a rapid rate now that the price of bulbs has dropped, and micro-LED displays may soon become the dominant digital display technology. So there might be a time when incandescent bulbs and LCD displays are thought of in the same way as vinyl records and rotary phones. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oakton and Cameron Kiefer. I want to thank everyone who supports the show over on Patreon. Your support helps make this podcast possible. I'd also like to thank all the members of the Everything Everywhere community who are active on the Facebook group and the Discord server. If you'd like to join in the discussion, there are links to both in the show notes. And as always, if you leave a review or send me a boostagram, you too can have it read on the show.